Okay, so we've seen that the transformation we've illustrated here, defined by this definition, can be represented by this matrix here. And we've seen at least a very strong indication that the transformation is indeed linear. And we're going to assume that's the case because if it's represented by this matrix, then since matrix multiplication is linear, the transformation has to be linear. In any case, T represented by this matrix, and we're going to let R2 be the standard basis, 1, 0, 0, 1, again, consistent with this picture. And remember that this vector maps here and this vector maps here. Vectors are on a line with slope -3. And we call this version of R2 space V and this one space W. So we're transforming space V to space W. So we kind of repeat all that, but we're going to say that R2 is going to be represented by the standard basis V1, V2 here. Okay, and that's going to be our vector space V. Okay, we transform V and we get these vectors as we've seen, easily calculated with the matrix product or the original rule. This vector and this vector are both in W, which is another version of R2. Now, if we start with the vector V, which is in R1 because V is C1 V1 plus C2 V2, where V1 and V2 are your basis vectors for the space V. Then, if we transform V, we get the same thing as if we multiply this matrix by V. Okay, now this is V, because V is this. By the linearity of matrix multiplication, this matrix product is C1 times AV1 plus C2 times AV2. And that's, of course, then C1 times what you get when you transform V1 plus C2 times what you get when you transform V2. To illustrate this, we use the example, and I've already drawn V here, and I've drawn W here, and I've got the transform vector T of V1 and the transform vector T of V2, which were illustrated completely here. Okay, if, for example, C1 equals 0.5 and C2 equals 0.2, what does all this tell us? Well, first of all, C1 times V1 is just 0.5 times this vector, which means it's going to be a vector that's half as long as this vector and in the same direction. So right here is C1 V1, which is 0.5 V1. C2 V2 is now, in this example, 2 V2. Well, that's going to be a V2 and you add a V2. So we have C2 V2 here. Which in this example is 2 V2. So that this vector V, C1 V1 plus C2 V2, is this vector here. C1v1 plus C2v2. Now what our work here shows us, again, agreeing that this representation works, and I think we've pretty well established that. Yeah, to do it in general, you have to do it with general symbols, but that's easily done, and we leave that as an exercise. Okay. Okay, C1, well, if we transform C1v1, this tells us that we're going to get half of what we get if we transform V1. Okay, so that the transformation of C1v1 is going to be half of this. That's going to come out to about here. So here is our transformed vector C1v1. V1 maps to this vector, so C1v1 maps to this vector, which is half as long. I'm not sure I got the half just right. I've got a bad angle here, but you understand what we're trying to accomplish. And then C2v2, this vector is twice as long as this vector, so C2v2 is going to map to a vector twice as long as this one and in the same direction, because it's a multiple twice that vector. Okay, so here's C2v2. It's the transformation of C2v2. And what we get if we add these two vectors is, well, C1, V1 has to be along this straight line. Now I've indicated again the line of slope -3. I think I mentioned that before, but here's a line of slope -3. T1, V1 and T2, V2 both lie on this line. We got two vectors transforming C1, V1 and transforming C2, V2 that both lie along the straight line. So if I add these two vectors, well, they lie along the same line. This one's a little bit longer than this one. We get the vector, and I'll draw it here, it's slightly offset. And hopefully it's visible. It's drawn in purple. Here's T of C1 V1 plus T of C2 V2. Add this vector, head to tail with this vector, we get this short vector here. And that equals, of course, T of our vector V, which is C1 V1 plus C2 V2. And we can calculate the vector. Okay? Leave it to you to calculate it. But just pointing it out, T of 1/2 V, remember the vector that's down here, is going to be half of this. It's going to be 0.35 negative 1.05. Twice this vector is going to be negative 0.6 and 1.8. Okay? So if we add the 0.35 to the negative 0.3, we get negative 0.05. If we add the negative 1.05 to the 1.8, we get 0.75. And I think one of my numbers there is wrong, but you can work out the numbers. And that's going to give us, again, a short vector here. Okay, if you write out the numbers, you'll see how it works. Now the main idea is then, again, that if we apply the transformation to a linear combination of V1 and V2, such as this, what we get is the same linear combination, the same C1 and C2 of this transformed vector T of V1 and this transformed vector T of V2. Okay, there are other ways to illustrate this. Again, this comes back to the idea that the rank of the transformation is 1, nullity is 1, because the rank of the matrix is 1 and the nullity of the matrix is 1. And we're going to develop that idea to quite an extent. The other thing is we note that when we transform V1 we get a much longer vector. When we transform V2 we get a slightly shorter vector. Okay? In other words, the transform V1 is significantly longer than V1, over twice as long. Transform vector V2 is not quite as long as V2. If we transform the sum of these two vectors, we get a pretty short vector. So we have the question, is there a vector that we could transform that would transform to the zero vector? Okay. Well, it turns out there has to be, because the nullity is 1. It follows that the dimension of the null space over here has to be 1, and we want to develop that idea. So, write the question here. Can we find a V that maps to the zero vector? That is, T applied to V is the zero vector. Or AV equals 0, 0. Now the equation AV equals 0, 0 gives you two simultaneous equations, and those simultaneous equations are homogeneous. So it's abbreviated, maybe a little hard to read. We say this leads us to two homogeneous equations in the two components x1, y1, or xy for this vector.